All, this is Dr. Mubin Sayed from drbeen.com. Welcome to one more show. Today we are going to talk about two topics. Number one, there is a study out of Iran that talks about the effectivity of bromhexine. Bromhexine and chymostat mesylate are some drugs that we really thought that they are useful. However, we had not yet found decent studies that could, back the effectivity or back the use of these drugs in SARS-CoV-2 patients or COVID-19 patients. So there is one study, it is a small study, but still it has very decent outcome. So I wanted to discuss that with you. So that is one, the effectivity of bromhexine, and it is effective. That is what we'll see. Second study that I want to see is about an antibody cocktail. And let me tell you the basic idea there, and then we'll look at the study together. The antibody cocktail, the problem so far that monoclonal antibodies may encounter is that when they bind to the spike protein on SARS-CoV-2, it is possible that SARS-CoV-2 will mutate a little bit and make the antibody useless. And so that is called the viral escape from the antibody, and that can pose a risk. So for example, if I am an antibody production company, I make a lot of monoclonal antibodies, and then the SARS-CoV-2 mutates and my antibody becomes useless, then that is a useless product. So the solution for that is to produce a cocktail of antibodies where there are more than one kind of antibodies that may bind to various parts of the spike protein. And so now the virus has to kind of change a lot so that it can escape all of those antibodies, which will become difficult, and the viral escape will become a problem for the virus itself, and we can neutralize it. So the second study is about a monoclonal antibodies that are produced by a company, and that we'll see how that works. This is very similar to Dr. Jacobson's company as well here, who have the cocktail of polyclonal antibodies. So that is what we're going to look at. Let us start. Hopefully everybody is good and doing fine. I'm going to share my screen and we'll go from there. Okay, so first this one, and welcome everyone. Hi, Cool Beans, Luffy, and Dr. Bean. So that is a comment here. Greetings, Margaret, back to you as well. James, back to you as well. Siddhartha, back to you. So yes, there's a question from Janet, TMPRSS2 receptor. Absolutely. So that is what we're going to talk about. Mbal says the big debate is now. Oh, I'm so sorry. So if you have left the big debate and are you listening to Dr. Bean, then I am really, really grateful to you. So I am not going to take a lot of your time. So you can go back to listening to the debate and let's start our discussion. So here, this is the first study. Let me just show you the links first, and then I'll go to the study so I don't take your time. Regeneron is the company that has made the polyclonal antibodies or the antibody cocktail. Here is their study that is there, and this is the study out of Iran. So I'm going to go and show you how that works. So we have worked on bromhexine before. Bromhexine, remember that this is, start from here. This is our cell. On the surface of the cell, we have ACE2 enzyme or the receptors. We know that the SARS-CoV-2 spike protein binds with the ACE2 receptor, but for it to bind there and then to bind with the cell to become internalized, we need, the virus needs our protein, which is also present on our cell surface. This protein is called TMPRSS2. This protein, the TMPRSS2 protein, in its all silliness, what it does is it primes the spike protein of the SARS-CoV-2. And what does that mean? It kind of cuts it in a way that the protein, the spike protein now splits into two portions. So one part now binds with ACE2 and the other part binds with our cell surface or cell membrane. And you can imagine that one part is holding onto the cell membrane and the other part is holding onto the ACE2 enzyme. And this then allows the virus to kind of internalize into the cell. So if the TMPRSS2, this goofy little protein, if this was not doing the priming part, then the virus will not have a chance to get into our cells. So if you see here, this guy is now silly, goofy guy is saying, yeah, you're welcome to the virus and I have primed you. So what happens is, once the virus is primed, here is the virus's spike protein. Spike protein has multiple domains. We have done this discussion in detail in Bromhexine video, so I'm not going in that much of a detail, but just this is the spike protein. Once it is primed, it has these various components. These components, if you see here, one component now binds to the ACE2, the other component binds with our cell membrane. The TMPRSS2 is taking a bow of saying, hey, you are most welcome. The end result is that this allows the virus to come inside the cell. So that is here. So if you see here, this is the virus, this is the TMPRSS2. The result is now the virus can easily become internalized. Then TMPRSS2 actually helps the virus inside the cell as well to liberate it from the phagocytic or the internalized particle inside the cell. So TMPRSS2 is like a buddy for the virus and just keeps helping it everywhere. And of course, we are not super cool about that, but it does it. Similarly, when the virus is trying to get out, the new viruses that are formed, when they're trying to get out of the cell and they need to detach from the cell, over there TMPRSS2 can also come and help them detach. So that is like their personal shepherd who is helping them everywhere to get out or get in the cell. Now, Bromhexine, I hope you remember this diagram from the previous lecture. I had made this thing look like a witch with a broom. So because hex is called a witch and broom is broom. So Bromhexine, this is the witch here. And if you see, this witch is now standing on top of TMPRSS2. That is, it is blocking it. It's a similar function like the what is that? The chemostat mesylate. And now the virus, the SARS-CoV-2, why is it crying here? It is crying because there is no TMPRSS2 to come and prime its spike protein and allow it to internalize. So now it is just standing out on the cell, trying to ring the bell and say, I want to go in, and it cannot because Bromhexine has neutralized the protein that will prime it. So that is the basic function of the TMPRSS2 blockers, that is chemostat mesylate and Bromhexine. Now, Bromhexine in the US, I think, is not available without prescription, but in other countries, it is available and it is cheap and it is effective. So now there are some, I don't know if it is available in the US over the counter or not, but here are some drugs that have Bromhexine in them. And now here is a study. This is a study that comes out of Iran. I'm going to quickly show you the study. So here is the study. Came out of Iran. This is the basic study. I have the link there. It would be interesting for you to read it. Here is what they did. It is an open label randomized study. So patients and doctors knew that this drug is being given. They had a small set of people, 39 in each arm. So there was a treatment arm and there was a control arm. They both had 39, a total of 78 patients. And the primary outcome they wanted to test was that what will happen to the ICU admission? Will we be able to reduce intubation? Will we be able to reduce the mechanical ventilation? Will we be able to reduce death if somebody is receiving Bromhexine? So what they did was both of these arms received the standard care that was available in the hospital at that time. That included hydroxychloroquine, but the dose was 200 milligram per day. So that was a small dose. Anyways, so in addition to the standard care, one group received oral Bromhexine, 8 milligram thrice a day till their stay in the hospital. So 3 times a day, 8 milligram of Bromhexine till they stayed in the hospital. And here are the results. I really love the results. First of all, please note, there were no major adverse events. So that is the important part, that fine, if a drug is going to be helpful, is it also going to be harmful? So Bromhexine did not have any adverse effects. And why I am so excited about this study, the reason is that till now, there was not much about Bromhexine. And I actually saw a study where they said it is useless. So I was kind of disappointed that TMPRSS2 blockers should actually work in theory from a mechanism's point of view, and there was no study showing it. So this is one study that is showing this one. So look at this, the primary outcome, ICU admission. Check this out, Bromhexine group, 2 out of 39. And keep in mind that there was 0 deaths in Bromhexine group. So 2 patients ended up in ICU, 5.1%, while in the standard care, 11 patients ended up in the ICU, which is 28%. So 5% versus 28%. So out of 100 people, 5 will end up in the ICU in case of Bromhexine, and 28 will end up in the ICU in case of standard care. Then intubation, 1 in 39, so 2.6%. On the other hand, 9 in 39, 23% were intubated in standard care. And then death, 0 out of 39, that is 0% death, and 5 out of 39, that is 12.8% death. P-values are reasonably good. P-values are reasonably good, so power of the study is fine, not too bad. I mean, if it was 0.0001, I would love it, but still these p-values are not bad. So Bromhexine first study shows that there is a good result. This is what I was expecting when I was discussing Bromhexine with us all in the Cool Beans. In chemostat mesylate, I was a little bummed that this is only available in Japan and not here. And now we have Bromhexine that at least it works and no major side effects. So that is one study that I wanted us to kind of look at. Now let's look at the second study. How are these cartoons? So whenever I make mouse with its cheese, I always make a man with the pizza as well, because I think that is only fair, that both of them are well fed. So let's look at the second study. This study, and let me say it out loud right in the beginning, I have no interest with Regeneron. I do not own their share. I am not influenced by them. I'm not sent a message by them. Somebody tweeted this link to me and I am looking at it together. The reason for this is that yesterday I talked about some company, that Australian company, INA, and somebody had put a comment that you should declare if you have an interest with them. I just cannot imagine why people are just after me saying I have some interest. I don't have any interest with them. So I don't have any interest here either. So other than they have something that is interesting for us to be safe and to be able to manage. So this is a study I would like, if you can read it. This is their outcome. And in the outcome, the basic outcome is this. Why this excited me is that this study was basically targeted to those folks who were immunocompromised. And I get a lot of comment from folks who are immunocompromised to say, what about us? How do we handle if we end up in this situation? So, for example, Hispanics, African American, and folks with the comorbidities. This study was specially done on those high-risk patients. So that actually gives us a new set of antibodies which can help those who are immunocompromised. So it's not necessary that African Americans are all immunocompromised or Hispanics are all immunocompromised, but that was one group that was used. And then another part of the group was those patients that had risk factors for COVID-19. And the basic summary of all of these outcomes, I wish they had a better writer who could make it a little easier. But what they're saying in all of those points is that when we gave the antibody cocktail to those patients who could not mount their own immune response, then this cocktail really helped them, very similar to those patients that could mount their own immune response and recover. So you can imagine that if you are immunocompromised, then this extra cocktail is very, very useful and brings the person at par in defense against the pathogen as a normal, healthy person. This is a very exciting news. So my request to you is that if you know someone who is immunocompromised, or if you know someone who is, let's say, in a high-risk group, then please share this study with them, share this link with them. They may even be able to enroll in the study and take advantage of it. So now let's look at what they have. So what this company did, and I have their PDF over here, and their PDF is quite detailed and quite large, but I wanted to share a focus on one part. So here is the PDF, very detailed process for how did they make the antibodies and what is the benefit of making those antibodies and what their process was. But I want to hone in onto something, and here is that. Number one, what they did was they took the B cells. B cells are the antibody making cells in us. B cells from human patients who had recovered. So convalescent patients. They took their B cells, and from their B cells, they extracted the antibodies that they were making against SARS-CoV-2. They also immunized some mice with the SARS-CoV-2 S protein, and then they challenged them with the S protein, and the mice in turn made antibodies too. This is a standard process. Then they combined those antibodies from both sources and refined them and found those antibodies that could bind better with the SARS-CoV protein. So out of hundreds and thousands of proteins, they kind of filtered out finally to 9 proteins and then 4 proteins. They wanted to do this. They did not want to find one antibody that is against the SARS-CoV protein. They wanted to find multiple antibodies that are against the SARS-CoV protein, so they can have pairs of antibody that would attach to various parts of the spike protein and then neutralize it and affect it. That way the virus, number one, will be neutralized, and number two, it would be difficult for the virus to create so many mutations because antibodies are attached to various parts of it. This is like somebody holds our hand and our feet and our head, and now we have to free ourselves from all of those, and it becomes difficult compared to somebody was just holding our hand. So they found those antibodies. They had hundreds of those. Finally, they found pairs of antibodies that could connect to various parts of the spike protein. And look at this diagram. In this diagram, here this blue part is the spike protein's part, that is coronavirus's spike protein, the part of spike protein that would bind with ACE2. So this blue one is that. And then if you see, there are 2 antibodies that they had created, this company had created. There are 2 antibodies that are bound to it. So they wanted to have pair of antibodies binding there. So what are these 2 antibodies? One is this green and blue. This is one antibody that binds to the protein at a different place. And then this yellow and red is another antibody that binds to the spike protein at a different place. So now there are like 2 little monsters that are attached to different parts of the spike protein. And now it's going to be difficult for the spike protein to attach to ACE2 and for the virus to create a mutation against both of them. So here is what they had done. So if you see this part, this is the coronavirus's spike protein. These are the 2 antibodies now that are attached to it at different locations. They both allow they both cause the spike protein to become neutral. It cannot bind with ACE2 anymore. So that is a good thing. In addition to that, they tested their protein or immunoglobulins for verified ADCP, which is antibody-dependent cellular phagocytosis. What does that mean? We have done this discussion previously. This is a macrophage or a dendritic cell, for example. This is an antibody that is bind to coronavirus. The macrophage or dendritic cell would have an FC receptor for this antibody, and it would bind with the antibody and eat up the virus with it. This is the same mechanism that is also used for antibody-dependent enhancement, where we are afraid that if we produce too many antibodies and they bind to too many viruses and then too much phagocytosis occurs, a lot of virus is going to end up in the cells and not get destroyed and cause them to be infected. And that is a concern with vaccine, correct? So the basic takeaway here is that our immune cells can bind to antibody, and then antibody is bound to the virus, and they both can be eaten up and destroyed. So they have confirmed that that mechanism will work with their antibody. So that's one. They have also confirmed that antibody-dependent cytotoxic activity. That means if an antibody is attached to a cell, then the natural killer cells or cytotoxic T cell will come and bind with that cell and throw perforins and granzymes and destroy those cells. So they have also made sure that their antibodies are able to elicit that response as well. So these are good antibodies. And finally, of course, as we say, these are effective antibodies in neutralizing. So those folks who are in the US, you know that sometimes police puts those boots on a car's tire, and so the car cannot move. So this is the same thing. Imagine these antibodies are like boots on a car's tire, and tire being spike protein. So that gets neutralized because the protein cannot bind with ACE2. And then finally, virus resistance escape is possible. And how is that possible? Because these antibodies are connected to various parts of the spike protein. Now the virus has to create mutations in more than one places, which is difficult for it to do simultaneously, and the virus would then get captured. Now, finally, what is the study? This is a study I just showed you the results for. In the result, the basic takeaway is that somebody who is not able to produce antibodies, when they are given these pairs of antibodies or the cocktail of antibodies, then they were able to behave or defend themselves against the virus just like other normal people, normal meaning other people with the normal immune system. So here they had 275 patients. 56% were Hispanics, 13% were African Americans, 64% had risk factors, for example, cancers or immunosuppressions or cardiac issues or diabetes or hypertension and so on. They had three groups of people. They were divided into three groups. One group got 8 grams of the antibody cocktail. Another group got 2.4 gram of the cocktail, and a third group had placebo only. And what they found was that within 7 days, the folks who were immunonegative, who were seronegative, that means they could not produce their own immune response, were able to take care of the viral load just like others. So that is the discussion for today. I hope you enjoyed it. I quickly plowed through this so that you can listen to the debates if you are interested in them. And that is what we have for today. I hope that you're all keeping safe. I wanted to, I think if you are okay, I wanted to do a discussion about various parts of management, prophylaxis, early management, late management, just like Math Plus protocol, because I'm receiving a lot of messages that what is the prophylaxis, and then for long haulers, what do we do there? So if that is something that you're interested, I think from tomorrow on, we can do individual sessions for how to do prophylaxis, how to do early management, and then how to manage the long haulers. I will skip the ICU parts because these are more complicated things, and ICU doctors should know better what to do. So with this, thank you, everyone. If you wanted to support my work, there is a link in the description for PayPal donations. You can use that. Please like, subscribe, and share, and I'll see you tomorrow. Stay safe and happy and blessed. Bye-bye.